সবাই শুনতে পাচ্ছেন?
জি স্যার।
Yes, sir.
So I think we can start our today's lecture. Today's lecture is on convolutional neural network. So I think you have already know about the neural network. In our last two lectures, we have discussed about the artificial neural network. In our today's lecture, we will cover the convolutional neural network. So at first, we need to say that the convolutional neural network is also a kind of artificial neural network. Specifically, it's a deep neural network with some convolution layers. So that means in our artificial neural networks, we already know that it has consisted of several layers, like the input layer, the hidden layer, the output layers. But in convolutional neural networks, we will see a new form of layers that is called the convolutional layer. So the convolutional neural network is an artificial neural network consisting of convolutional layers and also some other layers. Okay? So this lecture is taken specifically, part of this lecture is adopted from the lecture of University of Waterloo, Canada. So at first we need to understand that is the deep neural network architecture. So far we have already discussed. So if we can divide our algorithms in these four coordinates, specifically deep and shallow, some of the machine learning algorithms, those are follow the shallow architecture and some are in deep architectures. And if we can divide our algorithms in two categories like supervised and unsupervised. So if we can consider the deep and shallow in x-axis and supervised and unsupervised in another axis, then we can divide the learning algorithms in four coordinates. Some of the algorithms follow the shallow and supervised learning approach, like the support vector machine, perceptron. We know that the perceptron is a single neural nodes, okay? And then the boosting algorithms. Several boosting algorithms we have, like AdaBoost, gradient boosting, extreme gradient boosting. So those actually those follow the shallow architecture and supervised principle. And some of the machine learning algorithms, those follows the supervised architecture, but they have the deep architecture, like the deep neural network, the convolutional neural network, and the recurrent neural network. So the convolutional neural network, we will discuss it today. So it is actually follow the supervised principle, but the architecture is deep. Okay, that's supervised principle. So that means we need the supervised data set with the class levels, and it will follow the deep architecture. So that means usually the neural network or convolutional neural network, it has deep architecture. There are several other algorithms, those followed the deep architecture but the unsupervised principle, like the deep belief network, Bayesian non-parametric, sparse network, deep autoencoder. So those are deep architectures but follows the unsupervised principle. And some of the machine learning algorithms, those are actually followed the shallow principle, but they also follow the unsupervised principle. Okay? The architecture is shallow, but follows the unsupervised principle. Okay? Like GMM, it is Gaussian mixer model, restricted Boltzmann machine, sparse coding, and encoder neural network. So those are follows the unsupervised principle, but architecture is shallow. So in our today's lecture, we will cover the convolutional neural network, and it's specifically followed the supervised principle the architecture is deep. So if you can remember our deep neural network architecture, so this is one of the deep neural network architecture. You can see this is our input layer neurons, and then those are our output layer neurons, and we have three hidden layers. As I already mentioned in our last class, that usually shallow neural network consists of just only one hidden unit or hidden layer. But if we can add another, then theoretically that is our deep neural network architecture. So here in these deep neural network architectures, we have three hidden layers. And in our input layer, how many neurons we have? 1, 2, 3, 4, 5, 6, 7, 8. So 8 neurons in input layer. And how many neurons in our output layer? 1, 2, 3, 4. 4 neurons in our output layer. And how many neurons in hidden layer 1? So here is 1, 2, 3, 4, 5, 6, 7, 8, 9. Total 9 neurons in our first hidden layer. Similarly, 9 neurons in our second hidden layer, and 9 neurons in our third hidden layer also. Okay. So this is our deep neural network architecture. Now, if we want to count the parameter to learn this architecture, so how many parameters here to learn? That is, usually we call it learning parameters. So as we have in input layer, we have 8 neurons. And in hidden layer, this first hidden layer, we have 9 neurons. And this hidden layer, we have 9 neurons. This hidden layer also 9 neurons. And the output layer consists of just 4 neurons, okay? 4 neurons. So the learning parameters are the weights to learn, okay? Weights to learn. So each and every connecting edge, so that like this is, each and every connecting edge has a weight, okay? So like this one is W1. In this way, all the connections must have a weight, okay? So those are our learning parameters. So how many connections are there? How many connections are there? At first, we need to find out how many connections are there. That means each and every connection actually carries a weight. So it will be 8 times 9. So this is 8 times 9. And then the connections between these two, that is hidden layer 1 and hidden layer 2, is 9 times 9. And then these connections, 9 times 9 also. And these connections, we have how many connections? 9 times 4. Okay. So specifically, we can say that the first two connections, it is 8 times 9. So total 72. Okay. Then plus of, we have to think about 9 times 9. So 9 times 9. So this is 81 plus, again, for these two connections, that is hidden layer 2 and hidden layer 3. These connections, we have 9 times 9 plus. And last hidden layer to output layer connections, those are 9 times 4. Okay. So here is 81, here is 81 plus this one is 9 times 4, 36. So these are the total number of connections, and each and every connection carries a weight. So, and that weight must be learned. Okay. That means in each and every iterations, we will change the weights. So that's why those are called the learning parameters. In addition to this, okay, so like here 81, 81, 72, the total number, if we can calculate this, the total number of weights, 72 plus 81, So 72 plus 81 plus of 81 plus of 36. So here 270. You can see this is 270. Okay, 270. Now we can see here 270 connections. That means each and every connection has the weight. The total number of weights is 270. 270 weights. Total number of connections are 270. In addition to this, we also need to consider about the bias. Okay, that is the bias. It's a constant, and bias we have to add for each and every hidden layer neurons and output layer neurons. So that means we have to consider the bias for these connections. Except the input layer, we have to consider the bias. So each and every neuron, we have to consider a bias for that. Each and every neuron has a bias. Okay? That is the bias. We have to consider a bias for that. So similarly, the bias for the hidden layers also, hidden layer 2 also, each and every neurons, different bias for that. And also we have to add bias for our hidden layer 3, okay? Each and every neurons of hidden layer 3, and also bias for the output layers. So except the input layer, we have to consider the bias for each and every neurons of hidden layers and output layers, okay? So that means then we have to think about how many bias in hidden layer 1. Total 9 neurons, so 9 biases. This is hidden layer 1. And for hidden layer 2, total 9 neurons, so 9 biases for hidden layer 2. And for hidden layer 3, how many neurons? 9, so 9 biases we have to consider. Plus of, for output layer, how many neurons? 4 neurons, so 4 biases we have to consider. So it is 31. So we have to consider 31 biases. Okay. Now, the total number of learning parameters we have to learn for this neural network, deep neural network architecture, it will be the number of weights plus of number of biases. Okay, so it will be 1 here and 0, and here is 3. So that means 3, 0, 1. The number of parameters.
স্যার বায়াসটা কিভাবে বের করেছেন আরেকবার একটু বলবেন?
আচ্ছা, বায়াসটা হচ্ছে প্রত্যেকটা হিডেন লেয়ারের জন্য একটা করে হিডেন লেয়ার এবং আউটপুট লেয়ার নিউরনের জন্য একটা করে বায়াস কনসিডার করতে হয়। কেন কনসিডার করতে হয় সেটা হচ্ছে যদি আমরা একটা লিনিয়ার ইকুয়েশনের কথা চিন্তা করি, y = mx + c, এটা একটা আমাদের লাইন ইকুয়েশন না, লাইনের ইকুয়েশন mx + c, এটা একটা লিনিয়ার ইকুয়েশন y = mx + c। এই যে প্লাস সি যেটা আছে এটা হচ্ছে y ইন্টারসেপ্ট বা কনস্ট্যান্ট। তো এখানে যতগুলো আমরা ইকুয়েশন এর আগের দিন চিন্তা করছি আর কি, যেমন হিডেন লেয়ার 1 এর যদি মনে থাকে তোমাদের, h1 = কি করছিলাম আমরা, x1 times w maybe 1 plus of x2 times w4, এটা ছিল h1, তাই তো, যদি মনে থাকে। হ্যাঁ, এটা একটা লিনিয়ার ইকুয়েশন, কিন্তু এই লিনিয়ার ইকুয়েশনে কোনো আমরা বায়াস চিন্তা করিনি, দ্যাট মিনস কোনো কনস্ট্যান্ট চিন্তা করিনি। কিন্তু ইভেন তো আমরা যদি একটা লাইন ইকুয়েশনে ড্র করতে চাই, we need to consider this plus c, okay? So that's why we have to add here the plus b. This is the bias, okay? So this is called the bias. So that's why each and every linear equation must include a bias, that is the b, to form the linear equation, to complete the linear equation. Okay. So that means we have how many hidden neurons here? Total 9 neurons. So we have to add 9 biases for each and every equation. কি মনে পড়ে নাকি?
জি স্যার।
এই লেকচারটাতে আমরা যেটা দেখছিলাম সেটা হচ্ছে H1, X1 W1 and X2 W4, এই যে H1 ক্যালকুলেট করতে গিয়ে এখানে আমরা বায়াস কনসিডার করিনি, কিন্তু actually we have to calculate one bias here. Okay, bias, we consider previously that okay, maybe the simplified version of this equation x1 w1 and x2 w2, but we have to add the biases. Actually later in this lecture I have already, yeah, here is the NN with bias. Okay, so not only the H1, we have to think about the bias here. B1, this is B2, like this. Similarly, bias also in output layer. This is BO. Okay, this bias, that means to complete the linear equation, we have to add a constant value, or you can see intercept. So that is our bias. Okay. So now that means how many neurons here in hidden layer 1? So 9 neurons. We have to consider for each and every neuron just one bias for that. So 9 neurons, that means 9 biases. So that's why we have to add the biases also. So total we can see here 301 total number of neurons, or total number of learning parameters we have. Okay, that means we need to update each and every time in every iteration. We have to update the 301 number of values, and then maybe in after many iterations we will find out that the each and every parameter has some specific value, like the y equal mx plus c. We have to determine the m, that is slope, and we have to determine the c. C is our y-intercept value to find out a line. Okay, so similarly here is also the same thing. That means to uh, converge this problem, that is the given data set, we have to find out that is the w and b. Okay, w and b. So that's why we have to apply many iterations to find out the exact value of w and exact value of b. We have to learn those parameter values to find out the convergence of this. That means the accuracy is high for that case. Okay, now this is the case for our deep neural network architecture. So this is our deep neural network architecture. Now the question is whether we need all the connections or not. There are too many parameters. Okay, too many parameters, too many connections are there. Specifically, though this is a deep neural network architecture, but the number of layer we have considered just only the 3, and number of neurons we have considered for each and every layer just only 8 to 9. So though this one is deep neural network architecture, but corresponding to the real world deep neural network architecture, this is actually very small. So that's why if we think about like learning one image, so if we want to learn like here, this is an image. Okay, this is an image. So how many there is the input parameters we have in this image. So think about like it has this image has the resolution like 1024 times 1024. Okay, so this is the resolution of this image, 1024 1024. It means that we have total 1024 times 1024 1024 times 1024. So 10,48,576. Okay, so more than 10 lakh, more than 10 lakh. So more than 10 lakh. So that means more than 10 lakh pixels we have. So in this image, there is more than 10 lakh pixels we have. So it means each and every pixel, if you can know that there is each and every pixel, each pixel has 3 components. 3 components. Each pixel has 3 components. That is R, G and B. So we have red part, green part, and blue part. Okay, red, green, and blue for this color image. Okay, so that means maybe the value of the red will be 128. Maybe the value of the green will be 112, and maybe the blue is 101. Okay, so that means for each and every pixel we will have like 3 components: red, green, and blue. So that means if we consider about these pixels, this image, so that means 3 times we need that 3 times 10 lakh plus. That means 30 lakhs. Okay, so that means if we want to design a deep neural network architecture, to learn this image from its raw data, then we have to add 30 lakhs or at least 10 lakhs. Okay, at least if you consider about our grayscale image, at least the 10 lakh neurons, in input layer. So that means for this case, if we just try to input the raw image to our neural network, so that means it has total or more than 10 lakh neurons, 10 lakh neurons in just input layer. Okay, so that's why for the case of our image processing or image analytics, if we want to design something, some model utilizing the deep neural network architecture, then if we try to feed the raw data to the neural network, then the neural network would be very large neural network. And for that case, think about like the 10 lakh plus, 10 lakh plus the neurons in our input layer. Then we have to consider at least the 10 lakh in hidden layer 1, 10 lakh in hidden layer 2, 10 lakh in hidden layer 3. So in this way, then how many parameters do we have to learn just for a single iteration? Okay, so that means it's too much or it's huge for that case. Okay, so that's why we have to think about like whether all these connections are necessary or not. Okay, or we can say in another way, how can we reduce the number of connections or number of weights? So that's why initially we can think about the convolutional neural network and how it will reduce the number of parameters to learn. At first, we want to discuss it. Okay, and first thing is we can see that this is the image, but whether all those pixels are necessary or not. So what we want to learn from this image? In this image, there is a bird. We want to know the name of this bird, or we want to classify the bird. So that's our target. Okay, target is to classify this bird. So that means there are several pixels. So like the pixels here, pixels there, pixels there. So actually there is no information about on those pixels. So do we need to learn the parameters related to those pixels? Actually not, because those pixels, they have no information of this part. So that's why we can easily exclude those pixels from the images as they have no contribution to learning this part. Okay. So that's why what we can do, maybe we can slice this pixel in several windows. Okay, slice this pixel in several windows like this way. Okay, and now if we can think about like, okay, we want to learn the back of this bird. Then we want to learn the wings of this bird. We want to learn the tail of this bird. We want to learn eye of this bird. We want to learn the leg of this bird. Okay, so that means that's why can we introduce something like the bake detector? Okay, can we introduce something like eye detector? Introduce something tail detector? Okay, instead of learning the whole image, can we introduce some of our learning, that is, we can say kernels? Okay, so like the bake detector, eye detector, wings detector, leg detector, tail detector. Okay, so that means several detectors we want to utilize here instead of learning the whole image. Then what will be the benefit for that? Okay, what will be the benefit for that? So on that case, this detector, it will search the bake in this image. Another detector, it will search the eye in this image. Another detector will search maybe the tail in this image, like this way. Okay. So instead of learning the whole image, on that case, it will learn a part of this image only. Okay, the part of this image only. So there may be possibility that if we try to do this, then we can reduce the number of parameters to learn this model. Okay, but the thing is, if we think about like this is the first picture, this is another picture, then bake will not be in the fixed position. Like in this case, for this part, the bake is here, in maybe the upper left corner of our image, but another bird is there. The bake is at the middle position. So then, how can we think about finding out the bake? On that case, we have to search the bake to this whole image, and we have to search the bake to this whole image also. Then maybe we will find out the bake for this bird in the upper left corner, but for this bird we will find it in the middle. That means we have to just search the bake using this bake detector everywhere of this image. Okay, maybe you can say at first this position, then this position, after that maybe this position, after that the next position, after that the next position, and after that maybe this position. The bake detector will try to find out the bake from this image like this way. Okay. Similarly for eye detector also. Okay, eye detector also, it will search the whole image utilizing the window. Okay, window, or we can say the detector or kernel. Okay, so then how it will reduce the number of connections? So now, at first we need to think, that is, how can we find out the bake? How can we introduce the bake detector? And what will be the bake detector for that? So that's why a special layer, we call it the convolutional layer. The convolutional layer, what it will do, it will apply. So this is, we can say, a detector. This is our detector, and this is the image. So what we will do, we will apply some convolution operation as we divided the image to some passes. So this is the first pass, and this detector will apply convolution operation here with this paths, and then it will find out some value. It will find out some value. So this value is actually the feature. Okay, this value is actually the feature for the back, feature for the eye, feature for the wings. Okay, so this is the back detector. It will try to find out the feature for the back to this whole image, and for that it will shift. Okay, it will shift the position, and again it will apply the convolution operation. So as I already mentioned, a CNN, or convolutional neural network, is a neural network with some convolutional layers. So that means this is one of the layer. Okay, the bake detector, it will apply searching to the whole image. So this is one kind of layer. Okay, so we will utilize this layer. A convolution layer has a number of filters. Okay, so filters. This is the filter is actually the detector, and does the convolution operation. Okay, so it will do some convolution operation. Then what's the convolution operation? We will discuss it later. Okay, as I already mentioned about the convolution layer, so we can see that this is the input image. Then we have to apply some convolution operation. So for that, what we need a detector. Okay, detector like this is one is detector. Usually this detector is called the kernel or filter. Kernel or filter. So then we have to decide the dimension of our filter. Like this can be considered about the 5 by 5 filter. It means 5 by 5 pixel. So each and every time it will do the convolution operation to this image of size 5 by 5. So that means the space size of this image will be 5 by 5. So each and every time it will find out the feature for this 5 by 5 paths. And then it will shift to next position. So that means next pass, again 5 by 5. And this filter will search the bake here. That means it will apply the convolution operation and it will find out the feature for the bake. Okay. So in this way, what it will do for each and every filter, like this is the bake detector filter. So it will find out the feature map for the bake. So this is the feature map for the bake. Similarly, we have to try another filter. So this filter is our eye detector filter. So it will also create another feature map for the eye. And another filter, maybe we can consider this one is our wing detector filter. So it will create another feature map. So those feature maps are the output of our convolution operation. Okay, output of our convolution operation. So this is our the first layer convolution. Then again, what we will do, we will apply the subsampling. The subsampling means we want to reduce the number of connections, okay, number of features. So that's why, so we will apply the subsampling. Subsampling, that means the larger image we want to produce that is the smaller size image, smaller size images. So that's why this is called the subsampling or pooling. Okay, so we will apply some pooling. The pooling, it will actually find out. It is also kind of the filter, so it will reduce the size of the feature maps. So here is the reduction of the feature maps. Okay. So after that, again, we will apply the convolution operation here. Convolution operation. So this is the layer 2 convolution. This is first layer convolution. This is second layer convolution. And again, it will find out the feature maps. And then again, we will apply the subsampling or pooling. So we will get a smaller size feature maps after this convolution. Okay, so in this way, several convolution and several pooling operations we can perform. As we know that each and every convolution actually try to find out the features. That means it will try to find out the feature of the back. It will try to extract the feature of the eye. It will try to extract the feature of the wings and legs. Okay. So okay, in this way, finally we will get the features. Okay, finally we will get the features. Finally we will get the features, and then we will combine all those features in this fully connected layer. So that means we will make those feature one dimension. This is in fully connected layers, and then this fully connected neural networks will apply for the classification. Okay? For the classification, for the output. That means, okay, what kind of bird is this? Okay, and what's the name of this bird? whether it is bird or maybe this is another cow. Okay. So we can see several convolutional neural network design. So one can consider just the neural network like input and fully connected. Okay, so that means input layer and the fully connected. Fully connected layer is just the neural network. Okay, just a neural network. This is a classifier. And now this is the first convolutional neural network. Here we can see input, then convolutional, then ReLU, then FC. FC is fully connected. Fully connected again, fully connected. It is a neural network, just neural network. Okay. So input, that means we can say this is the image, and then apply the convolution layer. Like here, this is the convolution layer, and then we will get these feature maps. There after that, there is no subsampling. Directly, we can see this is the ReLU. ReLU is activation function, like the sigmoid function. ReLU is also one kind of activation function. Okay? Rectified linear unit, that is called the ReLU. So the sigmoid, and this is the ReLU activation, and then after that, that's fully connected. So this is one kind of neural network. Someone can consider another kind of convolutional neural network, that is input and then convolution, then ReLU, and then pooling, so 2 times. Okay, so that means convolution, ReLU, pooling, convolution, ReLU, pooling, so 2 times, and then fully connected layer, and then ReLU, and then fully connected again. Okay, so someone can design the convolutional neural network like this way. Someone can design differently, like here. The input, then convolutional, ReLU, convolutional, ReLU, convolutional, that 3 times. Okay, so that means this architecture, it follows the 3 times, and then the fully connected, then ReLU 2 times, and finally the fully connected layer. So that means the network you need to design for your problems, solving your problem. It will totally depend upon the users. Okay, based on the problem, the given problem, and then based on our that is the user defined neural network. So that's why you will find out that many networks already proposed by different researchers. Like for sentiment analysis, you will find out the Sentinet. So it means this researcher proposed a convolutional neural network architecture for the sentiment analysis. And this design is totally different from the design of others. Okay, so like different others. So that's why they propose this architecture as a Sentinet. Okay, someone will propose something like the EMONet. EMONet. So EMONet, it means that for the emotion classification or emotion recognition, someone proposed the convolutional neural network architecture for the emotion classification, and that design is different from the design of any other existing designs. Okay, so that's why it is called the EMONet, emotional convolutional neural network architecture. So based on your problem, you can propose some neural network architecture like this way. Okay, for finding out or for solving your problem. Specifically, those are convolutional neural network. The convolutional neural network, this one is the heavily used neural network architecture in all domains. Specifically, this one is better for image processing, object recognition. But nowadays, the convolutional neural network is used everywhere, not only the image, but the signals, the time series analysis, and then also our audio processing, and then the natural language processing, okay, NLP also. So based on these convolutional neural networks, there are several architectures are also developed. Those are very popular architectures. Like you may heard the name of the VGG16, VGG net, actually, the VGG16, and then Inception version 3, MobileNet, Exception. So those are the the transfer learning architecture. Those are actually based on the convolutional neural network and its different forms. And then after that, the transformer architectures. So based on the convolutional neural network plus the attention layers. Okay. So again, the transformer architectures. The transformer architectures are used in NLP. It is used also in the vision. Okay, computer vision. That is called the vision transformers. But again, the base, the convolutional neural network architecture. Okay. Now we have to understand the convolution operation. Okay? Convolution operation. Specifically, the convolution operation we have to perform between two functions. Okay, that is f and g. So f and g. That means we can see there is a convolution. It's an operation. It's an operation like the other mathematical operations. It's an operation, mathematical operation. The convolution, it means that is if we want to, if we have two functions like f and g, and we can perform the convolution operation between those functions. So specifically, if we consider f one dimension and g also the one dimension, that means kind of the array. Okay, so one dimension, or we can say consider those are vectors, f vectors and g vectors, and we can perform the convolution operation. It means that the convolution operation is an integral of the product. So integral of the product of two functions. So product of two functions here is, we can say f is one function, g is another function. So we want to find out the product of these two functions. Product of these two functions, that is the f and the g, product of these two functions, after one is reversed and shifted. Okay? After one is reversed and shifted. So that means between those two functions, we can consider one of the function like g. It is reversed. Okay? It is reversed, and then it will shift. So it will shift. So this is integration. Okay, so the integral of the product of two functions. So this shifting, it will happen from 0 to t. Okay, from 0 to t. So the limit of the integration, we can see it is the lower limit is 0 and upper limit is t, and we have to perform this integration here. Okay, it's the convolution, one kind of integration of the product of two functions when one function is reversed and shifted. So what does it mean? It means that if we consider one vector, there is our f, one vector, and another vector is g, and we want to perform the convolution operation. This is the c. We want to find out the output of this convolution operation between these two functions f and g. So what it will do? At first, we have to reverse one of these functions. Okay, let's say we want to reverse the g. We want to reverse the g. So then f is there. This is our f. This is our f. And this is the g. G is shifted. Sorry, g is reversed. So g is reversed. It means 3, 4, 1. Instead of that, it will be 1, then 4, and then 3. So here it is. You can see this is our 1, 4, and 3. And then it will start from the 0. Okay, so this is our 0 position. 0 position. So that means we can see this part is common between these two functions at first. So 3 times 1, we have to multiply this 2. Multiply this 2. So that means 3 times 1. So 3 times 1 is 3. So this is in after performing the convolution between these two functions. The first element you will get the 3. Then what we have to do? The shifted 1 bit. Okay, shift this. So after shifting, we will get there is 4, 3 now. So these are the common. So that means we can say 1 times 4 and 4 times 3. Here is 1 times 4 and 4 times 3. So this is 4 plus 12 is 16. So in C1, in convolution 1, so we will get the 16 here. Okay? 16 here. So we will get the 16. And then again we have to shift. So we can see that we have shifted another bit, and now 3 is in common. 1 times 1, 4 times 4, 2 times 3. This is 23. So this is this value we will get after convolution. And then again we have to shift. Then we will get 4 times 1, 2 times 4, and 5 times 3. And this is 27. And then again we have to shift. So here is 2 times 1 and 5 times 4. 5 times 3, this is 22. And again we have to shift. After shifting, we will get 5 times 1. Here is the 5 times 1 is. And then we have to shift. And if we shift further, then actually there will be no common value. That means we cannot perform the dot products of this two. Yeah. So then this value will be our the convolutional value. So after convolution operation, we will get 3, 16, 23, 27, 22, and 5. So those value we will get. So this is actually one-dimensional convolution. Okay, one-dimensional convolution. We have considered the f and g as one-dimensional vector. Now, if we think about like the two-dimensional, okay, so the two-dimensional. So on that case, you have the input will be the two-dimensional. Like this is f. F is two-dimensional, and the filter is also there is g also two-dimensional. So g also two-dimensional. Now here is also the same thing. There is dot product and also we have to shift. Okay. So as I already mentioned that is for the case of the image, we have to divide the image in passes. Okay. So here we can see the filter. This is our G. This is filter. Filter is 3 by 3. So we have to divide our image 3 by 3 paths. So here is the 3 by 3. 3 by 3 paths. And now we have to perform just the dot products. Okay, so here is we can see 1 times 1. That is 1 times 1 plus of, and 0 times negative 1. So 0 times negative 1 will be 0 plus, then 0 times negative 1. Again we will get 0. Then 0 times negative 1. We will get again 0. And then this 1. Here is 1. So 1 times 1. So that means we will get the 1 plus, then here is 0. Here is negative 1. So that means we will get again 0 plus, this is 0. And this is negative 1. So we will get 0 plus, this is 0. And this is negative 1. So 0 times negative 1 is 0 plus, here is 1. And here is also 1. 1 times 1 is 1. So that means if we apply the convolution operation here, between this G, there is filter 1, and the first path we have, then we will get from 1 times 1, this is 1, here is 1, and here is 1, that is 3. We will get the 3. Okay. So for this operation, we will get 3. Okay. That means we will get the 3. Then what we have to do? We have to shift this one. Okay, we have to shift this one. If we consider about the just shifting one bit, so that means we can see this is just one bit. This one bit shifting is called the straight of 1. Straight 1. So that means we consider each and every time it will shift just one bit. So that is the value of the straight equal to 1. So then what we will get? We will get the next, again, next 3 by 3. Okay, next 3 by 3. Next 3 by 3. Then again, it will perform the same convolution operation. Okay, so that means here is 1 and here is 0. So we will get 0 plus, then the next 0, and here is negative 1. So that is 0. Then plus, then here is 0, and then negative 1. So that means 0 plus, then this is 1, and here is -1. So that means 1 times -1, that means we will get the -1 plus, and then 0 times 1, we will get 0 plus, then here is 0, here is -1. So if we perform the multiplication, then we will get 0 times 0 plus, then this 0, and here is -1, that means 0 plus, and then here is the negative, here is +1, and here is the -1. So +1 times -1, it is a -1 plus, here is 1, this is 1, and this is also 1. Okay, so it is +1. So after adding this, here is +1, here is a -1, cancelled out, and -1. So that means we will get the -1 after this computation. Okay, so here we will get the -1. So in this way, again we have to shift 1 bit. Okay, so we have to shift 1 bit. Maybe after that we will get this patch, and again we have to perform the convolution operation. Then we will get some value here. Okay, and then again we have to shift. Maybe you can say this time we can shift it here. Okay, so we will get this patch, and then again we can perform the convolution operation. So we will get the value again here, and then we can see that is again we can shift 1 bit. So if we shift 1 bit, then we will get the patch like this way. Okay, we will get the patch like this way. So now we can see we have just only 2 feature here, this one and this one, 2 feature or 2 feature, but we need the 3 by 3, but actually the value we receive here just only in first 2 columns or first 2 features. There is no value here, okay, in our third. So what we can do, we can add just only the zeros there, just only zeros there. Okay, so if we add the zeros for our convolution operation, so this is called the padding. This is called zero padding. So we pad this image using just zeros. So that's why called is zero padding. So that is zero padding. Okay, so we can consider the zero padding, and again after zero padding we can perform. Sometimes we may not consider zero padding. Okay, zero padding, and we can maybe apply the convolution operation till our size of the image. Okay, till the size of the image. So that means till this image size of the image. So that means on that case we will not apply the zero padding, but we can also consider the zero padding. Okay, so we have the option for that. Okay, if we apply the zero padding, then again we have to consider, okay, the first, after considering the first zero padding, we will get this one, and again we have to shift, and again we can maybe consider another layer of zero padding. Okay, so now we have to shift the window down. Okay, shift the window down. So that means next we have to think about our window. This one is our window. So this is the patch we have to think about. And again the same filter. For that case, we will get again the value here. Okay, some value here. And then again we have to shift it in right side. That is a straight is 1, considering a straight is 1. So considering the straight 1. So that means the patch we will consider the next patch will be here. Okay, and for that, after applying the convolution of operation, we will get some value, and again shift the right side. That means a straight we have to consider 1. If we consider a straight equal 1, then it will shift just 1 bit. If we consider the straight equal 2, it will shift 2 bits at a time. Okay, so that means the straight is just how many bits you want to shift at a time. Okay, So okay, so for the filter one, we will find out an output. Okay, output. So this output is called the feature map. This is our feature map. So this is our feature map one, first feature map. So feature map. This is the first feature map for the first filter. Similarly, we can apply the filter 2. Why filter 2? As I already mentioned that, okay, filter 1, maybe you can consider this one is our back detector. So this one is our back detector. Filter 2 is our eye detector. Okay, so that means we need several detectors. So that's why we have to consider several filters here. For filter 2, again, we have to perform the same, start from the beginning. Okay, beginning, because we need to find out the eye to whole images. Okay, the whole image. That's why we need to search it to the whole image. And that's why, again, we have to start from the beginning and utilize the filter 2. Okay, filter 2. So in this way, maybe we will get another feature map, that is feature map 2 for the filter 2. If we consider similarly, maybe you can say 25 filters, then we will get the 25 feature maps. Okay, 25 feature maps. So as you can see, okay. So for first filter and state equal 1, considering this image, actually we will get this value. Okay, so this is our feature map 1. Feature map 1 for the first filter. So if we consider about another filter, then we will get again another feature map. Okay, another feature map. In this way, for each and every filter, we will consider several feature maps. Now, if we think about the color image, okay, as I already mentioned that for the color image, actually each and every pixel has the color values. Okay, like red, green, and blue component. So this is the red component, this is the green component, and this is the blue component. So that means we have to apply the filter 1 on the red component, and maybe for the blue component and for our green component. Okay, and we will get the output for the red component, green component, blue component of filter 1. Similarly, for filter 2, we have to apply on these 3 components also. Okay, for the color images, if we consider about the color images. Then now, so as I already applied the convolution operation, specifically the 2D convolution, you can see this is our image. This is 6 by 6 input. Input is 6 by 6, and we have applied the feature map, 2 feature maps. This is feature map 1. That is filter 1. This is filter 1, and this is filter 2. 2 filters. So we will get 2 feature maps. Okay, so we can see 2 feature, one in background and another one is in foreground. Okay, so we can see 2 feature maps we have. 2 feature maps we have. Now, as I already mentioned, that if we apply the filters, then it will reduce the number of connections. Then we can see how it actually reduce the number of connections here. So think about this is image, and this image is 6 by 6. Okay, 6 by 6. So 6 by 6 means we can see if we think about the construction of the equivalent neural networks or deep neural network, then input must be consist of 6 by 6, actually total 36 neurons. Okay, so that means in input layer we have to consider 36 neurons. So you can see this is the first neuron, second neuron. Actually, we can, as I already mentioned in neural network lecture also, and input layer neurons, usually we call it, those are not neurons but the placeholders. Okay, the placeholders. So here these are the placeholders. So x1, x2 up to 36. So that means 36 total 36, x1, x2 up to 36. So in our input 1, this value we have to pass. And in second neuron, we have to pass this one. In this way, for 36, we have to pass this value. So x1 means 1, x2 means 0. Similarly, x36 means 0. Okay. So for neural network design, we have to think about like that. Design is like this way. Okay. Now, if we can consider our convolutional neural network design. So for convolutional neural network design, you can see that filter 1, and this is the 6x6 image, and it will create this feature map. This is feature map 1 for the filter 1. Okay, and after performing the convolution operation, we will get the 3. We will get this 3 for this operation. Okay, get this 3 for this operation. So that means the input, we can see the input here is 1, 0, 0. So here is, we can say 1, 2, 3, 4, 5 up to, in this way, 36 total. Okay, for the input image, total 36. So this is 1, this is 2, this is 3, 4. Then we can see 5, 6, then maybe 7, 8, 9, 10, then 11, then 12, then this is 13, 14, 15, 16, like this. Okay, so 4, this is 5, this is 6. Okay, then 7, 8, 9, 10, 11, then 12. Okay, so the input we can see here, for this fully connected, the at position there is 1, we can first, this is 1, and then second position, this is second position is 0, third position is 0, fourth position is 0. So here is 1, then second position 0, third position 0, fourth position 0. And how about the fifth position? Fifth position is also 0. So here is the fifth position. That means we have to add 0 here. Then sixth position is also, we can see sixth position. 1, 2, 3, 4, 5, 6. Sixth position is 1. Okay, sixth position is 1. So sixth position is 1. And again, seventh position is 0. So seventh position is 0. Eighth position is 1. So this is 8. 8 is 1. 9 is 0. 10 is 0. 10 is 0. 11 is 1. Okay, so 11 position, this is 1. Then the 12th position, we can see the 12th position here. 12 is 0. Okay, so this is 12. 12 is 0. So 12 is 0. And then 13 is 0. Here is the 13 is 0. 14 is 1. And 15 is also 1, like this. Okay, so these are the positions and their inputs. Those are input values. Now these are the filters. Okay, so filter, and we can see this is 1, negative 1, negative 1, like this. And after performing the convolution operation, we got the 3. Okay, so here is the 3. Perform the operation. Now actually, to get the 3, what are the values we have already considered as input? So to get the 3, we consider that this is 1, and then 2, and then 3. So that is 1, 2, and 3. So these 3 values. And then 4, 5, 6, no. Then 7. This is 7. 7, 8, and 9. So we can see here 7, 8, and 9. These values we have utilized. And then 7, 8, 9, 10, 11, 12, then 13. Okay, and 13, 14, and 15. So here is this 13, 14, and 15. So those are the values specifically utilized to get the 3. Okay, get the 3. Now you can see there is we have to shift this one just one bit, considering the straight one. Straight one. After shifting, we will get the next value. Okay, that means next value is our -1. So here, after shifting, we will get the -1. And for that case, we will utilize the values like in this case, this is our 2, 3, and 4. So here is this 2, 3, and 4, these 3 values. And then 8, 9, and 10, these 3 values. And then here is the 14, 15, and 16. So these values, okay, to get this one. So whether we have to change the filter values or not, actually we didn't change the filter values. Okay, these filter values. Those filters, these are actually our weights. In our convolutional neural network learning, we will change these weights, the filter values. We will change the filter values. We will learn the filter values. Okay. So in case of our traditional deep neural network architecture or convolution or just artificial neural network architectures, we cannot share the weights. But here we can see we are sharing the weights. Okay, we are sharing the weights. So we can see there is the same weight, the same value. We are utilizing to find out different feature maps, different feature map values. Okay, so in this case, the same value we can see that is the same weight. So this weight, the one, this weight, we have used to generate 3, specifically this one, the red one. Okay, and also the same weight, that is 1, the same weight we have utilized to generate the -1, the same weight. We can see this one. Okay, the red one. The red means maybe the weight 1. Here is also the same weight. That means we can say weight 1 is utilized here. Similarly, weight 2 is utilized for finding out the 3 here. This one is our weight 2, and same value we have utilized here. This is weight 2. Okay, so that means the weights are shared. But in our deep neural network architecture, we cannot share the weights. So each and every values, you can see this value, we cannot share the weights here. So the weights are different for different connections. Okay, so that means that's why here one question we have asked: can some of these be shared? That means same weight we can utilize to find out different values. Okay? But in convolutional neural networks, we can think about the shared weights. Okay, shared weights. So if we can share the weight can be shared, then we can reduce the number of parameters. Okay, we can reduce the number of parameters. That means after utilizing the shared weights, we can consider about the fewer parameters are required for that. Okay, and another thing here is only connected to the 9 inputs, so not the fully connected. So for producing this value, we have connected just 9 neurons. Okay, so 9 neurons. We have connected the 9 values. So instead of connecting the all, like in this case, actually for each and every value, this one for fully connected neural networks, to produce this one, we have to have the connection from each and every input. Okay, each and every input. So here is the 36 inputs. To produce this value, we have to consider all the 36 input. But in case of our convolutional neural network, we can see just we have to consider this 3, 3, and 3, total maybe 9 inputs instead of 36. So here is also we are reducing the number of parameters. Okay, number of parameters in convolutional neural networks. Okay, so that means the fewer connections we are using, and then another thing is we are sharing the weights also in convolutional neural networks, and the last one is also that is the pooling operation or subsampling operation we are performing. So subsampling also reducing the number of weights. Okay, subsampling. So that means instead of utilizing the the bar of like 1024 by 1024 image, if we subsample this, then we will get the same image but in lower resolution. Maybe you can say it will be 128 by 128. So even though we can subsample this one, but the actual image is not distorted. Okay, so the actual, we can still recognize the same image, the same bird. So how do we do that? We will discuss about it, but how can the CNN, that means the convolutional neural network, compress the fully connected network in 2 layers, specifically how the CNN is benefited from benefited if we compare to our that is the deep neural network architecture, how the CNN reduces the number of parameters. So we can say 3 ways. The first is reducing the number of connections. The second is it is sharing the weights, and third is utilizing the max pooling for reducing the number of pixels. Okay, so these are the 3 ways the CNN, a convolutional neural network, compress the fully connected network, or you can say artificial neural network. So I think we can stop here today. In our next lecture, we will discuss about how to construct the convolutional neural networks, how to construct that, and the number of parameters, how to calculate the number of parameters necessary for each and every convolutional layer. And then we will discuss also that is how to determine the output size of each and every convolution, and how to determine the output size of each and every pooling operations. Okay, thanks everyone.